Hello everyone. In this video we will learn about the properties of definite integrals. These properties are very useful in finding the definite integral of some of the functions. Before going to the properties, we must learn that if d by dx of a function fx is equal to fx, that is derivative of function fx with respect to x is small fx, then the antiderivative or the privative or the integral of fx dx will be equal to capital Fx. The same concept we will be applying in some of the properties, and the first property here is integral of fx from a to b is same as integral of ft dt from a to b. The proof of this is a to b fx dx. We know the integral of fx is capital Fx and the limit is from a to b. Will it be equal to fb minus fa as per the definition of definite integral? If we take this right hand side here, integral of ft dt from a to b is also equal to ft from a to b, which also will be fb minus fa. From these two, we find that integral of fx dx from a to b is same as integral of ft dt from a to b. What does it mean? It means that if we change the variable but the limits remain same, then the value of definite integral does not change. The second property is the limit from b to a fx dx is same as minus a to b fx dx, and the proof of it can be taken as, if we take the left hand side here, that is b to a fx dx is equal to fx from b to a. As per the definition of the definite integral, will it be fa minus fb? If we take minus common, will it be equal to fb minus fa, which is equal to minus a to b fx dx? What does it mean? It means if we interchange the limits, then the sign of the value of this will change, numerical value will remain same. Generally it is seen that the upper limit is greater than the lower limit, but in case we find that the upper limit is less than the lower limit, in that case we can make use of this property. The third property is integral of fx dx from a to b is equal to the sum of fx dx from a to c plus integral of fx dx from c to b. It means the interval can be broken into some of the sub intervals, then this definite integral will be equal to the sum of these two. This we can understand in two ways. The first way we can understand this by the concept of representing the area. See, if it is from a to b, then we know that definite integral from a to b represents this complete area or not. In case we take any point c somewhere in between a and b, then the integral from a to c fx dx will represent this area or not, and the integral from c to b fx dx will represent this area. If we find the sum of these two, will be equal to the integral of fx from a to b. The second concept we can have is the definition of the definite integral. If we start from the right hand side, this is a to c fx dx plus c to b fx dx. This is fx from a to c. This is fx from c to b. If we apply the limits, this will be fc minus fa. This will be fb minus fc. We find here that this fc and fc cancel. And this is equal to fb minus fa, which is the integral of fx from a to b. If we generalize the property, we can write a to b fx dx is equal to a to b1 fx dx plus b1 to b2 fx dx plus so on bn to b fx dx if we are dividing it into n subintervals. The fourth property is integral of f of x dx from a to b is same as integral of f of a plus b minus x from a to b. It means in place of x, if we apply the sum of the limits minus x. To understand the proof of it, we go with the right hand side, which is integral of f of a plus b minus x from a to b. And we have to use the substitution method here, and we substitute a plus b minus x equal to t. When we differentiate this, we will be getting minus dx is equal to dt, or we can say dx is equal to minus dt. We have to change the limit also according to t. So we know when x is equal to a, t will be equal to a plus b minus a, that is b. When x is equal to b, t will be equal to a plus b minus b, which is equal to a. It means this will be minus b to a f of t dt. And we know if we interchange the limits, the sign will change. So this will become plus a to b f t dt. Now if we use the first property here, this can be written as a to b f of x dx, which is the left hand side. The fifth property is zero to a fx dx is equal to 0 to a f of a minus x dx. For the proof of this property also, we can go with the right hand side, which is 0 to a f of a minus x dx. And we use the substitution. We substitute a minus x as t. If we differentiate, we will be getting minus dx is equal to dt, or we can say dx is equal to minus dt. What about the limits? When x is 0, t will be a minus 0, which is a. And when x is a, t will be a minus a, that is equal to 0. Applying this here, we will have this as minus a to 0 f of t dt. If we interchange the limits, the sign will change. This will be plus 0 to a f t dt. Applying the first property, we can write this as 0 to a fx dx, which is the left hand side. It means integration of function fx from 0 to a is same as the integral of f of a minus x from 0 to a. We use the same property in the second pattern also, that is when we have 0 to pi by 2, it means a is pi by 2, fx dx is same as 0 to pi by 2 f of pi by 2 minus x dx. The sixth property is 0 to 2a fx dx. It has two different values for different two conditions. That is twice of 0 to a fx dx. That is if f of 2a minus x is equal to fx and its value is 0 if we find that f of 2a minus x is equal to minus fx. For the proof of it, we can write 0 to 2a fx dx as 0 to a fx dx plus a to 2a fx dx. We have broken this particular interval into two subintervals and we know the property that it can be used as the sum of the two integrals. Second part. If we go only for the second part, we find here a to 2a fx dx. If we substitute here 2a minus x is equal to t, or we can say x is equal to 2a minus t, then differentiating we will be getting dx is equal to minus dt or not. But we have to convert the limits also according to t. So we get here when x is equal to a, t will be equal to 2a minus a, that is a. And when x is equal to 2a, then t will be 2a minus 2a is equal to 0. It means this can be written as a to 0 minus dt in place of this, so minus can be taken out. And this x can be written as f of 2a minus t dt. If we interchange the limits, we know that sign will change. So this can be written as plus 0 to a f of 2a minus t dt. Now using the first property, t can be replaced by x and the value will be same. So we can write this as 0 to a f of 2a minus x dx or not. And now if we substitute this in this particular part, then we will get here 0 to 2a fx dx will be equal to 0 to a fx dx plus 0 to a f of 2a minus x dx or not. And now we can go for these two cases. First case, that is if f of 2a minus x is equal to fx, then substituting this value here, will we get 0 to 2a fx dx will be equal to 0 to a fx dx plus 0 to a fx dx, which is equal to twice of 0 to a fx dx. If we go for the second case, I'll write the second case here. Second case, if f of 2a minus x is equal to minus fx, then 0 to 2a fx dx will be equal to 0 to a fx dx minus 0 to a fx dx or not, because this is minus fx. They cancel each other and this comes as 0. The seventh property is minus a to a fx dx is equal to, this also has two answers. One is twice of 0 to a fx dx if fx is even function, and it is 0 if fx is odd function. You know what is an even function, what is an odd function. We say for even function f minus x is equal to fx, and for odd function, we know that f minus x is same as minus fx. When we go to the proof of it, we can write minus a to a fx dx as minus a to 0 fx dx plus 0 to a fx dx. It means we have divided this interval in two subintervals. Now we take only the first case. That first case is minus a to 0 fx dx. If we substitute here x as minus t, will we get dx is equal to minus dt? Now we have to find the limits for t. When x is equal to minus a, t will be equal to a. And when x is equal to 0, t will be equal to 0. So here we will have minus a to 0 f of minus t dt. If we interchange the limits, sign will change. So this will come a plus 0 to a f of minus t dt. Using the first property, we can also write this as 0 to a f of minus x ds, because the value will be same since we are not changing the limits. Applying this here, we will get therefore minus a to a fx dx is equal to 0 to a f of minus x dx plus 0 to a f of x dx. This we can write as 1. Now we go for both the cases. We say case 1, if fx is even function, it means f of minus x is same as fx. Then minus a to a fx dx will be 0 to a fx dx plus 0 to a fx dx, because this has become fx. And we can write this as twice of 0 to a fx dx. In the second case, we have fx is odd function. Odd function means f of minus x is equal to minus fx. Then our integral minus a to a fx dx will be equal to 0 to a minus fx dx plus 0 to a fx dx. They cancel each other and this comes as 0. This way we can prove all the properties of definite integrals. To understand the application of these properties, we will discuss some of the problems. And the first problem we are taking here is integral of root of sin x upon root of sin x plus root of cos x from 0 to pi by 2. To find the solution of such problem, we can consider this as I. And now if we apply the property, we can write applying the property 0 to pi by 2 fx dx is same as 0 to pi by 2 f of pi by 2 minus x. Applying this property, we will get I equal to 0 to pi by 2 root of sine of pi by 2 minus x upon root of sine pi by 2 minus x plus root of cos of pi by 2 minus x dx. Is it or not? Then we know the formula sin 90 minus theta or sin pi by 2 minus theta is cos theta, and cos pi by 2 minus theta is sin theta. So we will get this as 0 to pi by 2 root of cos of x upon root of cos x plus root of sin x. What we find? That if we write this as 1 and this 2, we are finding in 1 and 2 both the denominator is same. So if we add these 1 and 2, adding 1 and 2. Since both are I, this will give you I plus I, that is equal to 2I will be, denominator is same. So LCM is root of sin x plus root of cos x. The numerator also will be root of sin x plus root of cos x. And these two will cancel each other. The limit is from 0 to pi by 2. It means we are getting here 0 to pi by 2 1 dx, which is equal to x from 0 to pi by 2. If we substitute the limits, we are getting this as pi by 2 minus 0, that is pi by 2. This is the value of 2I. It means I will be equal to 1 by 2 into pi by 2, that is pi by 4. Like this we can find the solution of this particular problem, and the value of this comes as pi by 4. One more problem we can discuss here, that is 0 to pi by 4 log of 1 plus 10x. To find the solution, we consider it as I and write this as 1. Applying the property, zero to a fx dx is equal to 0 to a f of a minus x dx. We get here I will be equal to 0 to pi by 4 log of 1 plus 10 pi by 4 minus x. We know the identity 10 pi by 4 minus theta is equal to 1 minus 10 theta upon 1 plus 10 theta. Applying this here, we will get 0 to pi by 4 log of 1 plus 1 minus 10x upon 1 plus 10x. This is equal to 0 to pi by 4 log of, if we take the LCM here 1 plus 10x, we will get 1 plus 10x plus 1 minus 10x. This 10x and 10x cancel, and we are left with 0 to pi by 4 log of 2 upon 1 plus 10x. This we can write as 2. Adding 1 and 2, we will get 2I equal to log of 1 plus 10x into 2 upon 1 plus 10x. The limit is from 0 to pi by 4. How this has come? Because we know log m plus log n is log m into n. This 1 plus 10x and this 1 plus 10x cancel each other. So we are left with 0 to pi by 4 log of 2. A log 2 is a constant. So this can be written as log 2 into integral of 1 dx from 0 to pi by 4. And we know the integral of 1 is x. So we can write this as log 2 into x from 0 to pi by 4. Substituting the limit, we will get this as pi by 4 into log 2. This is the value of 2I. Therefore, I will be equal to 1 by 2 into pi by 4 log of 2, which is equal to pi by 8 log of 2. This is the answer. Like this, we can apply the properties of definite integrals to find the solution of the problems. In the next video, we will be learning about application of definite integrals in finding the area of region. Thanks for watching my video. If you have any comments or doubts, leave them in the comment box and I will get back to you.